Hi, the lecture today is about l'hospital rule. You have to get familiar with this French name. A more understandable way of talking about this is to talk about the indeterminate forms. From the beginning of the calculus class, you remember that you were studying the limit problem, and perhaps you came across questions like this. Say you had a limit of x squared minus say 16 over radical x say minus 2 as x approaches 4. Question, the beginning of calculus 1 was, how would you find this limit? You learned some techniques for handling this, and we are going to have a bit of a faster method of handling this question and questions that are somewhat more complicated. Let's go back and review what happened there and what was the problem. When x comes very close to 4, of course, x squared goes close to 16. So as x comes close to 4, numerator is going to come close to 0. Denominator, radical x, when x is very close to 4, radical x is going to be close to 2. So radical x minus 2 is approximately 0. So when x is very close to 4, you have something that is close to 0 divided by something else that is very close to 0. This eventuality, which is like 0 over 0, is referred to as an indeterminate form. That is, if you look at this fraction 0 over 0, you cannot make sense of it at all. You cannot assign any number to 0 over 0. As you remember back in elementary school, they would tell you don't divide by 0, and they scare you of all kind of devils and whatever else that's going to show up if you divide by 0. Well, by the time you come to calculus, they tell you that division by 0 is not all that bad. If you have a number, say 2, and you divide it by 0, the answer is either plus or minus infinity. So division by 0 of a non-zero number leads to infinity, either positive or negative depending on how you arrived at 0. But 0 over 0 is totally ambiguous. We cannot assign anything to it at all. Here is a rather simple-minded way of showing that you cannot assign any number to 0 over 0. You remember what this fraction means to us actually. If you have 6 divided by 2, you write it as 3. By that you mean that 6 is equal to 2 times 3. So if we consider this as our understanding of a division, we can come here and kind of justify 0 over 0 to be just any number we want. Suppose I want to show that this is equal to, say, 17. How can I show that? Let me clarify this thing by coloring my zeros. Here's a red 0 and here's a blue 0. This fraction was equal to 3 because we could say numerator is equal to denominator times the quotient. So how about here? Can I say the numerator is equal to denominator times the quotient that I had? Well, of course it is so. 0 is equal to 0 times 17. But then of course whatever number I put here still will be true. So 0 over 0 cannot be assigned any number because it's totally meaningless. It is not in this category. So it requires a separate discussion. 0 over 0 is an example of indeterminate form. At the beginning of the calculus class, you would do this by factorization or rationalizing and such steps. Now we have a more refined way of approaching these. The L'Hospital's rule itself is based on the mean value theorem. It can be proved based on that, and I go ahead and explain the procedure and then write the theorem itself. If you want to take a limit of a fraction where the numerator and denominator are approaching 0, excuse me, this was 16, such as this one, numerator and denominator are separately approaching 0 at that point, we can go ahead and differentiate numerator and differentiate the denominator take the same limit from that. If this limit exists, L'Hospital's rule tells us it's going to be equal to the limit of this expression. Well, taking derivative is typically a lot less painful than doing all those factorization that you had to do. We go ahead, so limit of that is 2x, excuse me, derivative of x squared minus 16 is 2x. Derivative of radical x, you remember what was derivative of radical x? That was 1 over 2 radical x. Now when x is approaching 4, there isn't anything ambiguous or indeterminate about this. This is 8 and this is okay. Here this numerator, when x comes close to 4, is an 8, and denominator is going to become square root of 4 is 2, so this is going to be 2 times 2 is 4, and it all boils down to 32. As opposed to doing what? Well, at the beginning of a semester you would have done the following. Perhaps you say a limit of x squared minus 16 over radical x minus 2 is equal to, let me go ahead and simplify my writing a little bit. You start by your fraction, you go ahead and factor this, x minus 4 times x plus 4. Denominator, you take it, multiply by your conjugate, since you are multiplied by the conjugate, you better multiply with the same thing in the numerator, multiply with radical x plus 2. So what have I done so far? This is just my fraction that I had at the beginning. I just factored it. I factored the numerator, and this piece I am multiplying by the conjugate of my radical expression in the hope of cleaning out the radical. So now I have x minus 4 times x plus 4 times radical x plus 2. Denominator, when you multiply them, you get x minus 4. Now when you get that, then you can go ahead and say I cancel out the culprit, and all I'm left with is what I need. So right now I go say, oh no, I'm done. I can take my limit. If you want to take a limit of this one, you might as well take the limit of this one or limit of this one, which turns out to be, after you simplify these things, all that you're left with is this. When x approaches 4, you have 8 times 4, and that is 32. So you get the same answer, but there are some gymnastics required here to get that to that answer. For more advanced function, these methods are not going to work either. If you are dealing with sine, cosine, exponential, logarithm, and all of those, We don't have the luxury of all these differentiations, luxury of these factorizations in that case. So L'Hopital rule really is a more powerful method. Let's go ahead and apply the method to a couple of other problems. Here one question is exponential of 3t minus 1 over t. Take a limit of that as t goes to 0. Well, let's first make sure that this is an indeterminate form. When t goes to 0, what happens to the numerator? We'll have exponential of 0 minus 1. Denominator is just 0. Well, exponential of 0 is 1. 1 minus 1 over 0. 0 over 0. Well, we just formally carried out all these calculations. Of course, none of these things make any sense by themselves. We couldn't divide by 0. Just indicating that if you just carry out all these calculations, you end up with an indeterminate forms. If it is so, and if the functions are differentiable, you can go ahead and apply L'Hopital's rule. So I differentiate numerator and denominator. The first few times perhaps we write down what we are doing. Later on we just skip this step as well. We just differentiate. Well, what is the exponential of 3t? Do you remember that? Exponential of u, if you want to differentiate it, is the exponential of u times u prime. So the exponential of 3t, u is 3t, its derivative is going to be 3. How about derivative of t? That is just 1. Now I need to write the word limit everywhere. Limit, again, t goes to 0. When t goes to 0, this is 1 again times 3. That is 3 divided by 1, and the ratio turns out to be just 3. Notice that we couldn't apply this style to this problem, at least not in an easy way, and L'Hopital rule comes to rescue. Now, L'Hopital rule is also applicable to cases where you are dealing with infinity over infinity. This is another one of the indeterminate forms. You have seen again problems similar to this at the beginning of the semester, and we are doing a similar problem now. Now let's go ahead and pick a question that will exemplify this one. There aren't that many simple easy questions with that flavor. You either have to work with tangent or logarithm and such at the points of their discontinuity, or you deal with functions as x goes to infinity. That's another possibility. Here's a question. Figure out the limit of exponential of x over x cubed as x goes to infinity. Well, as x goes to infinity, what happens to the function exponential of x? If you remember, graph of exponential of x is something like this. Exponential of x, like 2 to the x and such, exponentially grows to infinity. So when you go to infinity, as x goes to infinity, function or the y value also goes to infinity. In this direction, you escape to infinity as well. Exponential of x goes to infinity. So does x cubed. Graph of x cubed, again, you might remember graph of x cubed looks like this. This is x cubed, and that was exponential of x. This one goes to infinity also. So we have a large number in the numerator and a large number in the denominator. What would be the ratio of this to that? The question is, which one of these two infinities is going to win over the other one? Well, L'Hopital's rule clarifies the situation for us. We go ahead, differentiate. Derivative of numerator, well, that is itself. Derivative of denominator, it makes a difference in the denominator. Now, whatever problem we had here is still here. This is also infinity over infinity. When x goes to infinity, both of these are infinity. So we go ahead, do the game one more time. I differentiate. Derivative of exponential of x is exponential of x. Derivative of 3x squared, that is 6x. Again, we are stuck with a similar situation. When x goes to infinity, that's still going to infinity, and x, as you're saying x going to infinity, 6 times x also goes to infinity. So we apply this one more round. Numerator always stuck at what it was. Denominator is 6. X goes to infinity. Well, now this is no longer indeterminate form because only numerator is infinity. If this is infinity divided by a number, answer is going to be infinity. So what that means, that exponential of x wins the race against x cubed, and the ratio tends to infinity, meaning that if you graph this ratio, graph at the end just keeps going up, just like these two graphs did. There is something to learn here. It doesn't really matter what power we had in the exponent here. So long as you keep differentiating, you arrive at the same conclusion. L'Hospital's rule assures us that this procedure is valid, and that final limit is the limit of this. So far we have learned example of 0 over 0. This was one indeterminate form. Another indeterminate form is infinity over infinity, which is resolved in the same style. The other indeterminate forms are resolved by converting them to one of these two styles. An example of this is the example 0 times infinity. How do we realize this is an indeterminate form? 0 times anything is supposed to be 0. And a number times infinity is supposed to be infinity. So which one of these two is going to flavor the answer? This 0 is trying to drag it down, infinity is trying to drag it up, and there's no clear winner between the two of them. Let's see if we can solve this problem by solve a sample problem indicating this particular kind of indeterminate form. Let's consider the following example. Find limit of radical x times logarithm of x as x approaches 0 from the right hand side. What is this limit? Let's first explain that this is in fact an indeterminate form. When x goes to 0, what happens to radical x? Well, that becomes 0. How about logarithm of x? If you remember, graph of logarithm of x looked something like this. This graph of logarithm of x. At x equal to 0, logarithm of 0, what's logarithm of 0? When x approaches 0, logarithm approaches minus infinity. So when x approaches 0, this is minus infinity. This is 0. Who's going to win between these two? Would logarithm be powerful enough to pull us away and give us some number? Or is radical x so powerful of a 0 that's going to push everything to become 0? Or would the answer be somewhere in between? Well, the way we handle this problem is by converting it. How do we convert it? We have to make it either 0 over 0 or infinity over infinity. Here I choose to make it infinity over infinity. That is, I have logarithm of x. This radical x, I put it in the denominator like this. So I force it to go into the denominator. double check what you have right now, that if you simplify this, you get that expression back, that the radical x comes to the numerator. I want to take derivative of numerator and denominator, so I first prepare it. I just write it in the exponent notation. That makes my life a little bit easier. One more round. Now I go ahead and differentiate. I say limit of logarithm of x prime over x to power of minus 1/2 prime, again as x going to 0. Well, what is the derivative of logarithm of x? You know that well by now. It's 1 over x, and here derivative is minus 1/2 of x to power of minus 3/2. Remember, x is going to 0. We might as well try to clean this up. I'll write this as 1 over x. X to the power of minus 3/2 can be written in the numerator as x to the power of 3/2. 1 over minus 2, that's going to be minus 2. Simplify this thing one more time. I have minus 2. I forgot to write my limit words. Happens here because we are taking lots of steps. Limit of minus 2, x to the power of 3/2 divided by x to the power of 1/2, that is 1/2. Okay, now we are ready for the final punch. As x goes towards 0, what does x to the power of 1/2 gonna do? That's just, if you wish to write it one more time, let me write it one more time. Limit of minus 2, this is radical x, x going to 0. Well, when x goes to 0, radical x goes to 0, this whole thing is going to go towards 0. This is our final answer. So out of these two influences that we were talking about, 0 and infinity, in this case radical x completely won, and that the logarithm of x could not make a dent. Sometimes we get some intermediate answer, sometimes one side or the other side might win. By the way, what was the reason for this plus on top of 0? We are saying x is coming to 0 but staying positive. That is necessary for radical x to make sense and for logarithm of x to make sense. So that's just a technicality to keep us in the right domain for the problem. So far we have learned about 0 over 0, infinity over infinity, 0 times infinity. Now there are still other ones that are considered in indeterminate forms. One of these is infinity minus infinity. If you have difference of two infinities, you are dealing with indeterminate form. Why is the reason? Well, we don't know which of these infinities is stronger, and we don't know who is going to overcome what and what the answer might be. And here's an example. Find the limit of 1 over x minus cosecant of x as x approaches 0. Well, as x approaches 0, this expression 1 over x goes to infinity. Remember, who is cosecant of x? Cosecant of x is same as 1 over sine of x. Sine of 0 is 0. 1 over 0 is going to be infinity, so that is going to be infinity minus infinity. In fact, let's go ahead and write this thing in terms of sine. It'll be a little bit more clear as to what it is. 1 over sine of x, x is still going to 0. Okay, what do? We have to convert this to one of these forms. Here is an easy conversion. Just take a common denominator. This is going to be x sine of x, and numerator is sine of x minus x. Now I go ahead, pay attention that now when x goes to 0, this whole thing is 0. 0 minus 0 is also 0, so we really have reached 0 over 0 indeterminate forms. So this problem immediately got converted to 0 over 0. What do I do with it? Well, now I go ahead and apply the L'Hospital's rule. I say this is limit of, let's indicate what you want to do. You want to take differentiate this one and also differentiate this one. If this limit exists, it's going to be equal to the original one. Sometimes you have to repeat this differentiation several times. If at some level the limit exists, then you are done. If it is not settling down to a limit, then the process is not successful and you have to think of something else. We go ahead and differentiate this. Comes cosine of x minus 1, denominator derivative of first times second, that is sine of x, plus first times the derivative of the second, x times cosine of x. Notice x is going towards 0. We are still not out of the woods yet. Cosine of 0 is 1, 1 minus 1 is 0, sine of 0 is 0, x is 0, denominator is 0. We are still haggling with a 0 over 0 form, so I have to go ahead, differentiate one more time. Derivative of cosine of x is sine of x minus sine of x, derivative of minus 1 0, derivative of sine is cosine, derivative of x cosine of x, derivative of x is 1 times cosine is just cosine of x, derivative of cosine times x is minus x sine of x. Here x is going towards 0 still. Now I claim that we are done. Derivative, sine of 0 is 0. Denominator, this is 1 and that is 1, 2 minus 0. These are the terms that are left. So this expression turned out to be 0 over 2, which is just 0. So what we found out is that the difference between the 1 over x and cosecant of x, when x goes to 0, that difference is just 0. Notice that that was quite non-trivial, and let's go do another problem so that you don't misunderstand this. You don't think that the answer is always 0. Let's do, for example, radical x squared plus x minus x. Take a limit of this when x goes to infinity. When x goes to infinity, inside this radical is infinity, square root of that is infinity, minus another infinity. So at this level we are still dealing with infinity minus infinity form. How do we handle this? Well, we have to convert it to something else, and the conversion here the solution here is not going to be all that easier than what you might have done at the beginning of a semester using techniques from just plain algebra. So the steps I might go through might look a little bit contrived. What I can do here first to convert it to one of these previous forms, I can force an x out of this, that is, try to factor an x. How can I factor x? Let's go ahead and practice the basic portion of here. X squared plus x, I can write it as x squared times 1 plus 1 over x. So that might look a little bit odd to factor things like this. But I can push an x squared to come out inside the radical. Next, when x squared goes out, assuming that x is a positive number, this is going to be x times radical 1 plus 1 over x. So if I want to factor an x out of this, I'm going to get something a little bit unusual, factoring x. So I'm going to, this is equal to limit of x going to infinity. Factoring x out of the very first term is going to be 1 plus x. Factoring x out of the second term, I have just 1. Next step, this is now in the form infinity times I made a mistake here on my writing. Let me correct my writing. This was 1 over x. Okay. In the form we have now, at the beginning was infinity minus infinity. Now this is infinity, but this whole thing is 0. Do you see why? 1 over x, and x is large, this is going to be small, so 1 minus 1 is going to be 0. So by now, here is the form we are dealing with. Now one more round, we still have to do a conversion. Here is a conversion I choose to do here. I write 1 plus 1 over x minus 1 here and push the x in the denominator. How can I do that? I can write it as 1 over x. Now what I have is of 0 over 0 type. This is 0, this is 0 when x is infinity. I go ahead and apply L'Hospital rule. So this is radical 1 plus 1 over x minus 1. I have to differentiate all of that, and I have to differentiate all of this. X is still going to infinity. Denominator is not all that bad. Let me make more room maybe. Derivative of 1 over x, you go ahead, check that the derivative is minus 1 over x squared. Derivative of this one will be derivative of the inside of this, which is minus 1 over x squared, divided by that radical. Is that right? I hope your differentiation is fast and quick by now, that you can do these things quickly. You're still taking a limit. Let me explain what I just did. If you have radical u, you want to differentiate it. You remember that's u prime over 2 radical u. So u prime, derivative of that, is minus 1 over x squared, 2 radical u. I forgot to put my 2 here. It's 2 radical. Now we are going to do something a bit unconventional. In L'Hospital rule, one just keeps differentiating numerator and denominator, but sometimes it might pay to just look around, see if there is any other simplification you can do before you proceed any further. So here is a very useful simplification. If you don't do this, you're not going to get any answer. This minus 1 over x and minus 1 over x cancel each other out, and what we are left with is limit of, so this is not L'Hospital rule anymore. It's just a simple algebra simplification. 2 over 1 plus 1 over x as x goes to infinity. But when x goes to infinity, the 1 over x is going to go towards 0. We are left with 1 over 2. So after all this work, what we realize is that the difference between these two curves, when we go far to the right, is going to be 1/2. What do we understand by all of this? Well, our problem is all done. As far as the answer was concerned, we found that this limit turns out to be 1/2. But what does this whole thing really mean? Is there a way of seeing this without falling in the trap of all the algebra? Well, to see it, you need to go ahead and spend the time it takes to graph this whole thing and understand what is going on. So I'm going to divert attention a little bit to this issue. What does it mean to say that the limit of what was it, radical x squared plus x minus x is 1/2 and x goes to infinity? The way to understand this is to graph y is equal to radical x squared plus x. It might look like we are jumping from a frying pan into fire, from one problem into another one, but I'm hoping that you maybe remember this from your college algebra class. If you do, this is going to be quick, otherwise it's going to take just as long. Well, that is a hyperbola. The way to see that hyperbola, you can square both sides, rearrange it, and you'll see you get a hyperbola. The graph of that hyperbola looks something like this. To see the whole hyperbola, I go ahead and complete the other half of it. So up here what we have is a graph of y is equal to radical x squared plus x. Graph of y equal to x, that's going to be, well, that's easy. Graph of y equal to x. Here's the x. What we are claiming is that the distance between these two, the difference, this distance at the beginning, it's perhaps 0, and then as time goes on, this distance is going to settle down to 1/2. These two curves are going to travel in a way, you could say, parallel to each other. Their distance is going to be 1/2. Now, if you didn't remember how to graph this hyperbola and such, that's going to be a separate topic. We are not going to get into it right now. Might be a good idea you go back and review that from college algebra. How did you actually graph a hyperbola? We still have 2 more forms to go through. Let's review what we learned so far. We learned 0 over 0. We learned infinity over infinity. We learned 0 times infinity. Now we just learned infinity minus infinity. These are all ambiguous or indeterminate forms. The next one that we have is 1 to the power of infinity. That's a little bit harder than what we have so far. What's an example of this? Perhaps the most famous example that you have seen is the following: 1 over 1 plus x to power of x as x goes to infinity. This is one of the most famous example of this situation. Let's see what happens when x goes toward large numbers like going toward 10 and 100 and so on, this fraction goes towards 0 and the parentheses becomes close to 1, while this exponent running away with this. The best advice I can give you is to pick up a calculator and try to do this thing and see. For example, you might try 1.01 and raise it to power of 100. So take x to be 100, so 1 over 100 is going to be 100th, plus 1 makes it 101. Raise it to power of 100, see what you get. Try it with a larger number, x being 1000, see what you get there. Try it larger, 10,000. Here is the very first one, perhaps 1.1 to the power of 10. Look at the sequence of numbers. Do you have a guess what you're getting? Where do these numbers go to? Pause for a minute, use your calculator, make a guess, come back and tell me what your guess is. Did you see that you actually get the number E? That famous number. One of the explanations of it or definitions of it is this limit. Now, how do we go ahead and show this by the tools we have? This is going to be a little bit a roundabout way of going about doing things. We first take expression, say y, and set it to be 1 plus 1 over x to power of x. Our first task is to convert this to one of these two forms so that we can apply L'Hospital's rule. How can I make such a thing? Well, this is not directly accessible, but if I take a logarithm, it becomes more useful. So I go ahead, take a logarithm of this. If I take a logarithm of this, let's write first. This is a logarithm of 1 plus 1 over x to the power of x. Well, what does logarithm do? It brings the x up front. X logarithm of 1 plus 1 over x. So what is the advantage of this? When x goes to infinity, well, this is infinite. 1 over x becomes 0. Logarithm of 1 is going to be 0. So this form by now has reached infinity times 0 form. So I better go ahead and try to find this limit. Let's go ahead and find what is the limit of x times logarithm of 1 plus 1 over x as x goes to infinity. Well, we have to do another conversion for this. This is 0 times infinity. How can I convert it? Perhaps the simplest way I can convert this thing is to write it as logarithm of 1 plus 1 over x and divide it by 1 over x and try to take a limit of that. Now I apply L'Hospital's rule. L'Hospital's rule, I have to take a derivative of denominator. That's easy. Minus 1 over x squared. Derivative of the numerator. What's the derivative of logarithm of u? That was u prime over u. I have to take a derivative of this. Derivative of that is minus 1 over x squared divided by, here's the u, 1 plus 1 over x. Again, we have to take the limit of this expression. This is one of those places that we might as well deviate from L'Hospital and go and simplify some before we proceed. So I simplify these two, and what I get is limit of 1 over 1 plus 1 over x as x goes to infinity. That's it, easy. 1 over x goes to 0, and this whole fraction is going to tend to 1. So what do we have? Let's see. This was our original problem. We wanted to find this limit. We made a observation that perhaps you might have seen this limit before as a definition in one of the previous chapters on the explanation of exponential of x, but here we want to show this limit. We go ahead, define this function, take a logarithm of it. We have this function. Try to take a limit of that. In the process, we arrive at 1. Who is 1? That is the limit of logarithm of y. What we have found so far is that limit of this expression, when x was going to infinity, limit of this expression turned out to be 1. Now, logarithm of what number is it that is 1? So y itself had to be e. Y as a function of x was such that limit of the logarithm of it became 1. Y itself then has to be e. And now we find out that the expression was tending toward e. Okay, that was a bit complicated, and now we are going to move on to the last of these things that we have. Once again, let's go ahead and review 0 over 0, infinity over infinity, 0 times infinity, 1 to the power of excuse me, infinity minus infinity, 1 to the power of infinity, and the last in this list is going to be infinity to power of 0. This one also gets to be solved by methods just like the method I explained, that is, you convert it by taking a logarithm to 0 times infinity type. That is, you convert this to this type, and then you convert this thing back to one of these two, and you solve it by just taking logarithm as I explained. So we have these 6 different indeterminate forms, and we apply L'Hospital rule for figuring out the limits. Now go ahead and do some of the problems from problem list. Good luck and God bless.